Yeah. Okay, so then let's start with the colloquium. So welcome to today's colloquium. So we're very happy to have Eugene Polzik here today. He is from the University of Copenhagen, the Niels Bohr Institute, where he's also leader of Quantop, the center, the Quantum Optics Center, which he also founded. And his research interests in experimental quantum optics using light and matter include a quite broad range of topics, I would say, with applications in quantum communication and quantum sensing. His contributions, his seminal contributions, early contributions include, for example, a teleportation between light and matter or teleportation between atoms, and also the storage and retrieval of quantum states of light, also known as quantum memories, for example. He is a member of the Royal Danish Society of Science and a fellow of APS and OSA. He received several awards, of course, including the Herbert Walter Award and a Willem Investigator Grant. He's even a knight. And most recently, the breakthrough of the year of physics world. It was awarded for 2 papers, which were also based on earlier work of him. And today he will talk about microscopic objects in the quantum regime. So we are very much looking forward to it. And please give him a nice welcome.
Thank you very much. You know, I always wish my wife would hear all those nice words. But the thing is recorded, so I'll make sure she knows. Right. So it's a great pleasure to be here again, and there are wonderful old colleagues and friends. Well, old not by age, but by the time we know each other. Today's talk will actually be a rather review type. So I will try to cover 5 different topics shortly, and then hopefully you will find some of them interesting and look into more details. So the menu starts from one of my favorite subjects. Damn it. Those days. Quantum computing, quantum mechanics in the negative mass reference frame. I'll review what this is all about. Then I will discuss the experiment where we have implemented this idea and demonstrated entanglement of a mechanical oscillator with such a negative mass reference frame. And then I'll tell you about our efforts towards using this principle of measurements beyond the obvious Heisenberg uncertainty bound for gravitational wave detection. Then I'll switch gears a little bit and tell you a little bit about generating of a Fock state of a macroscopic mechanical oscillator. And then the last subject, if I make it all to the end, it will be our efforts towards analog quantum simulator. So as you see, it's a big menu. Let's get started. So in very introductory terms, I will be dealing with quantum oscillators today. And one of them is a macroscopic spin in magnetic field. You put a spin in a magnetic field, and suppose you orient the spin in the vertical direction classically, but there will, of course, be orthogonal quantum fluctuations. And in the collinear magnetic field, those quantum projections will be oscillating and will be formed as an oscillator. And the frequency of this oscillator can be tuned by magnetic field, and it can be originated in a ground state, as I always show you. So it's a wonderful device. Another, probably more intuitively familiar oscillator would be just a mechanical oscillator with the position and the momentum. And finally, light is, of course, also an oscillator, and we can assign x and p operators to the phase and amplitude quadrature of light. So that's the battlefield. And let's first talk about our mechanical oscillator. So we are dealing with mechanical oscillators with eigenfrequencies in the range of a megahertz. And if you take the energy of 1 megahertz quanta and compare it to the room temperature energy, or even the dilution refrigerator energy, you'll find that there is a lot of phonons in there. So you first need to cool it down to the ground state. And there are ways to cool it down to the ground state. And just to give you an idea, this is the type of the oscillators that we have. It's a small membrane, fraction of millimeter in size, which is embedded into the so-called phononic bandgap structure, which does not allow oscillations to leak out and thermal energy to leak in, or at least it prevents it from leaking in. So the oscillators we're talking about, they have a mass of about 10 nanograms. So the size of the 0-point fluctuations, that is to say, when you cool it to the ground state, will be of the order of a femtometer. For those of you who work with cavity quantum optics, measuring 1 femtometer is no big deal. You can measure much smaller sizes. So for this device, there is, of course, the Heisenberg uncertainty. Position and the momentum don't commute. So it looks like they cannot be measured with arbitrary accuracy. And if you try to do it, and you try to measure the x of this oscillator in the lab frame, in fact, you will be imposing the quantum back action on the momentum just simply by the radiation pressure of light if you want to measure it with light. And this is clearly seen in the rotating frame. So for instance, if at some point in time you are measuring the sine component, which is the x in my notation, you will put the back action onto p, and quarter a period later, you will be measuring p and putting the back action on x. And the more you measure, the more back action you have. So it looks like it's not possible to measure both x and p. And yet it is possible if you introduce a certain specific reference frame. So the specific reference frame, which we refer to as the reference frame with the effective negative mass, it can be, in fact, implemented by several systems. This whole business is by now 10, 15 years old, and people have come up with different negative mass systems. So the one that I like most is actually a spin oscillator. So imagine you have a collection of spin 1/2s. You optically pump them along one direction. Let's call it Z. So this is the macroscopic spin, Z. I remove a head from this thing. And the two orthogonal components are the quantum projections. So in the minimal uncertainty state with zero excitations, it will be the uncertainty blob here. And if I have n spins, then the uncertainty will have the size of the order of square root of n. And you can divide this by Jz, and you will arrive with the canonical commutator, which essentially means that the projections of the spin on those two directions are like canonical x and p. I seriously think you guys can afford a better system for this pointer. Okay, so if all my excitations are located around the northern pole, then I can look at this northern pole more closely, and it kind of looks like X and P. You know, the planet is large, it's almost flat, life is good. Still, imagine that I put one excitation into this system. So I made a spin flip, but I made a spin flip in such a way that it's not a particular spin that is flipped, but it's a superposition of any of those spins being flipped. So it's a large non-classical superposition of a single excitation. Well, it's a first Fock state, in fact. And you can believe me that the size of the Fock state is somewhat bigger than the ground state. And if it's somewhat bigger and the planet has a finite curvature, then the first excited state has a smaller energy than the excited state. That means that you put an energy in your oscillator and its energy goes down. Well, that's mathematically described as a negative frequency, negative mass, and negative elasticity all at once oscillator. And it, in fact, it can be very stable. It doesn't have to be unstable. Okay, so this is the, where did I lose this thing now here? This is kind of the way to write it down in the single spins representation. So it's a superposition of the first one flip, the second flip, the third flip, and so on. And in the same fashion, I can discuss, for example, entangled states, also collective states embedded into this big system. And now you put it in the magnetic field, and the whole thing begins to rotate, and now you have an oscillator. So, as promised, let's see how one can use this negative mass reference frame to observe both at X and P with, in principle, arbitrary accuracy. So you need to define this motion of your oscillator of interest in relation to this quantum reference, for example, this spin state. And this reference should have an effective negative mass, as I just mentioned. And you should generate an entangled state between the system of interest and the negative mass reference frame. And then you can perform the measurements of disturbance on your, for example, mechanical oscillator with the accuracy in both X and P of the mechanical oscillator, which is in principle unbound. So indeed, if I have a single oscillator, then its laboratory frame coordinate can be written like that. If I have two of them, and I make a measurement of the difference between the coordinates in the laboratory frame, then I have to write it down according to this equation as x of 0 minus x naught of 0 times cosine, and the same with p's, except for if the reference oscillator has an effective negative mass, then the derivative of the coordinate is not the momentum, it's minus momentum. And therefore, I get this plus, and now this commutes with that. And therefore, if I measure it once, I know the difference here and the sum here with arbitrary accuracy. And if I come microsecond later and measure again, if I find a difference in the cosine and in the sine amplitudes, then if I am sure that the disturbance only acted on my mechanical oscillator and not on the reference frame, then I know the disturbance in both X and P. So that's a simple trick. And one can actually prove that in order to get this to work beyond quantum limits, you need to have an entangled state between the system of interest and the reference frame, and the entanglement condition, for example, can be written like that. So I've already shown you this magic mechanical device, which has been developed by my wonderful PhD student Yegish Tsaturyan in collaboration with my wonderful colleague Albert Schlisser. And so the ground state motion at 300 Kelvin is of the order of picometer. And if you cool it down to 0, then it will be a femtometer. And the Q factor of the drum motion of this membrane is actually 10 to the 9. And this allows you enough time to run your experiments before a single thermal quantum jumps from the environment into your oscillator. So how do we make measurements? We use cavities. So we take, where is this thing? Now we got it because it's reacting to this thing. This is what it's doing. So maybe if I stand here, it'll be a little easier. Okay, so we have this membrane, which is seen here from the side, and it oscillates at 1 megahertz. And if a piece of dielectric oscillates in a standing wave of a cavity, then it, of course, modulates it. And if this disturbance or motion is due to some quantum effects, then you begin to see it in the spectrum of light, which goes into the cavity and, let's say, reflects from it. So more specifically, if you look at the quadrature phase amplitude of the light coming out, then of course you have a shot noise of light that comes in, that's natural. Then you have whatever force terms that are acting on this membrane, and in the absence of other sources of the force, there will be some thermal excitations, 0-point fluctuations, for instance, if you cool it down to the ground state. And on top of that, you have the back action of light. So this light acts on this membrane and through radiation pressure disturbs it. And this disturbance can be written as the response constant of the oscillator, and then the spectral response of the oscillator as well. So it can be a Lorentzian function, for example. And then here you have the x coordinate of light. So if the amplitude quadrature of light causes the radiation pressure, then it can be seen in the phase quadrature of light, right? So the amplitude quadrature bombards the membrane, and then you measure it by looking at the phase of light. So this is the whole trick behind this story. If I could possibly somehow cancel this back action, then I can measure the state of my membrane within principal arbitrary accuracy, because kind of the hierarchy for strong interaction is that this to that is the same as this to that. So if I have strong interaction and cancel this one out, then the force terms will be much larger than the shot noise of light. So this is the experimental demonstration that, in fact, if I look carefully at this noise spectrum of light, what I observe is a huge signal, which is due to the quantum back action of light. It takes years of hard work, of course, of the whole lab to observe quantum back action, which is that strong, but you can do it. And for comparison, this is the signal corresponding to the ground state of this system. So we're seriously dominated by the back action of light, and this is a good start. That's the device in the lab. We work at 10 Kelvin, which is almost room temperature. And inside this the fridge, we have this membrane, which is embedded into a high Q optical cavity. Okay, so what about the negative mass spin oscillator? Well, what about it? You have to have a large ensemble of atoms, right? As I told you, And our large ensemble of atoms is a big collection of spins in a gas state, which are essentially at room temperature, and they're held in a special environment such that the spin can run around at thermal energy, bounce off the walls many times, and still not decohere. So that's one of the tricks of the trade. And therefore, we can have a large ensemble of spins, which is strongly coupled to light even in a single pass. And the spin lifetime can be really, really long, even at room temperature. So you can calculate the Q factor for such an oscillator. It's large enough. And you can calculate this magic parameter, which is the Q times the energy of the single quantum, in this case, corresponding to this splitting of a megahertz or so, divided over kBt. And this will give you the number of periods of oscillation that you have to work before the thing decoheres. So if you have 10 to the 5 oscillations at 1 megahertz, then you have a good fraction of a second to play with this oscillator in whatever quantum state you make it. Right, and this is just an illustration how a single quantum can be made. So we can also test this oscillator separately just to make sure that it is in the quantum back action dominated regime. And this is done by the Faraday interaction and polarization spectroscopy. So if I have a spin, I put it in the magnetic field, it begins to precess. You send linearly polarized light through. Because of the Faraday effect, light is modulated, and you test this modulation here. And the point is that when this spin at some instant has a projection in this direction, you measure this projection, but then you put the back action into the orthogonal projection. I really cannot do it well. But okay, let me do it like that. So you measure in this direction, the spin is doing that. At some point, the spin instantaneously has this projection, you measure it, and you put the back action in this projection. Quarter period later, you're now measuring this projection, putting the back action into that one, and so on and so forth. So you make a measurement, and this measurement, you can do it in both cosine and sine quadratures, of course, using the locking amplifier, and it will contain the knowledge of the oscillator plus all those back action terms, again, which are shown here. The same as with mechanical. Oh, look, now it looks prettier. And this is again the experimental observation that you are dominated by the quantum back action as opposed to the ground state of the spin noise. Right. This is the mechanical system. Now we put those two things together. We can make a measurement of the mechanical oscillator and the spin oscillator simultaneously. And we put it in this negative mass reference frame. In more detail, you have this artistic rendering. So you have the spin oscillator, the mechanical oscillator, you make a joint measurement. And the goal is to cancel the back actions on the light. And we cancel them because quantum fluctuations which are imposed on the two systems are the same if you don't have losses in between. And the response functions are the same, but they have opposite signs. And so,
why are they the same? Yeah, we tune them.
We tune them. They tune them the same, of course. So Here is in the log scale, please notice, the first, we cannot tune the frequency of the membrane, but we can tune the frequency of the spins by magnetic field. So we first observe the membrane only, and this is in the log scale, and the checkered area is the back action, and it's well dominated by the back action. And then we test the same thing on the atoms. Here you cannot tell what is the sign of the mass of this oscillator because you're just measuring on one oscillator and you're measuring the variance. And it's also dominated by the back action because it's a log scale, so this is much bigger. And now what do you get when you tune the atoms on top of the membrane? Instead of adding the noise, you subtract it, and therefore you get the common back action on the joint system written on light, which is 6 dB below the sum of the two taken separately. So this looks like a good thing that works. And if you change the sign of the effective mass of the atoms by simply changing the optical pumping, then trust me, instead of this, you will have the sum of those two squared, which will be huge. Okay, so this works. And in the next experiment, we have used this back action cancellation to demonstrate that we can entangle the system of interest and the reference frame. And the entanglement condition is like that. Well, it goes to 0 in theory, but in experiment, it just goes below the level that allows you to publish. And this is what it is. So you have the atomic spin and you have the mechanical system. You send light through, we discussed it. And then what you measure as a function of time, so you turn on your interaction, you start with some state which has very large common variance, and you end up with the variance which is below the sacred level corresponding to the ground state of the two oscillators. So again, one oscillator is mechanical, the other one is the magnetic oscillator. And now I show you actually the experimental run where in the X and P frame, you observe the trajectories of both oscillators simultaneously. And if this thing works, we should be able to see that they are extremely close to each other. Amazing. Right? So they both run around inside their the thermal actually uncertainty. Why is it thermal? Because the back action is huge. If you take two entangled systems and just look at one of them, it's of course in the thermal state. It's only when you look at them together, they are in an entangled state. So this size is like half of the entangled state, which is a huge thermal state. But as time goes, the two states of the two systems, the gray one and the yellowish one, they follow each other because we generate this entanglement and we apply some feedback and they just go. So now, if one of them is affected by a measurement, by an external perturbation, we should be able to see this external perturbation in both X and P, in principle, with arbitrary accuracy. Okay, so this was an introduction. And now let's talk a little bit about what can the applications be. Applications can be whatever, wherever you are interested in measuring motion beyond the Heisenberg uncertainty principle, just do this. But the interesting stuff that we thought of was this gravitational wave detection. And of course, they're doing very well without us, but we thought maybe we can at least make them envious. So anyway, the gravitational wave detection, hopefully you read about it. So there is a 4-kilometer interferometer, and not one, but just many around the world. And you shine light on this interferometer, and then the light interferes, and the end mirrors of those interferometers are like many kilograms suspended mirrors. And when the gravitational wave comes, gravitational wave is a quadrupole wave, so it changes the space like that, and it misbalances the interferometer. And so those mirrors, those end mirrors, they just get a jerk in opposite phases. The interferometer is unbalanced. You measure the signal, get your Nobel Prize. But the point is that at the moment, so how do you measure it in the best possible way? Well, you shine as much light as possible, because the more light you shine, the better you can measure the small phase disturbance. But if you shine a lot of light, there is a lot of radiation pressure, and therefore you have a back action. And believe it or not, they are circulating 100 kilowatts of light there, and those 100 kilowatts have the shot noise radiation pressure, which is big enough to rock those kilogram mirrors so that they can see. Pretty surprising. Anyway, so what I'm showing you here is sort of the frequency band of the gravitational wave of interest. It goes from a few hertz to maybe a few kilohertz. And depending on where you are in the spectrum, rather where they are in the spectrum, at high frequencies of signals, it's short time observation, so they are limited by the shot noise of the measurement. At low frequencies, it's long observational time, and they are limited by the radiation pressure. And this is the best they can do at the moment. Well, there are tricks. I don't want to go into details here. They can move this left and right, but still kind of continuing along the same line. So the goal is the following. If you just measure on a single system, then the position of this mirror is the position at the initial point plus the momentum times time over the mass. And since the position and the momentum don't commute, you can minimize this product, and then you just express delta P over delta X, and you put them together, and you get the standard quantum limit of the measurement, which is given just by this simple expression. And the hope is that one can overcome it. And overcoming it can be done by putting this negative mass reference frame into one of the arms. At least this is what we hope for. So this is the spin ensemble in this glass cell at room temperature. It's not as simple as it looks, but it's a room temperature device. And so the point is simply that if the response of the oscillator, which is one of those mirrors, or both of them, looks like that, this is the normal oscillator response. If the response of my spin system with a negative mass is the same but opposite in sign, then obviously I can just cancel the noise across the entire spectrum. And you can write it down in extremely simple arithmetics. Well, in reality, it's more involved, but this is just a repetition of what I told you in the beginning, that if I want to measure X of one system in the reference frame of the other system, then it's the difference between the X's plus whatever velocities you get there. And if one of the masses is negative, then you have the difference of x's, the sum of p's, they commute, and therefore this measurement can be done in principle with arbitrary accuracy. The implementation of this thing is taking us by now the 4th year or something like that. And one of the difficulties is actually that, remember, in the first demonstration where it was a membrane and the atomic spin, we sent the same beam of light through the two systems because we want the quantum back action to be the same on the two systems. But here we can't do it because atoms want 852 nanometers and the LIGO people want 106. And none of them is negotiable. So instead of sending one and the same beam of light, you need to generate two entangled beam of light. One to interrogate the atomic system and the other to interrogate the interferometer. And so we've been busy building those systems, and there is a lot of technical details here. Yeah, this photograph is 1.5 years old, so they're smiling. They don't yet know what comes ahead. But what they managed to achieve is actually to generate one of the necessary conditions, and that's a beautiful entanglement between the two colors of light. So in this sense, we're ready. We're also ready in the other sense that we have the spin oscillator, which behaves quantum mechanically, not at 100 hertz yet, but at least at a few kilohertz. So we can run the proof of principle experiment, and we will not have any gravitational wave interferometer in the other arm, but we will simulate it with something, and then hope that if we can demonstrate something, then the people will start knocking on our doors. So that's what you call conservative estimate of improvement that we can demonstrate. All right. So now let me switch gears quite substantially and tell you briefly about generation of a very special state of this macroscopic mechanical object. So far, we've been talking about the continuous variable Gaussian, essentially, entangled states, EPR states. And now the goal is to generate a single Fock state of this motion. Right, so we have this device, and the size, just to give you an idea, so this is about 1 millimeter, and this is about 10 nanometers, so it's not exactly to proportion, but the size of the Fock state is like 10 to minus 15. So this is what we want to measure. So I already told you about the system. We have the membrane, we put it in the standing wave of the cavity, and the membrane has 0-point fluctuations of a femtometer. And as I already discussed, you can calculate how many periods of oscillation this device will stay in a quantum state that you generate before it's ruined by thermal fluctuations. And for a good Q that we have, it can be 1,000 oscillations. So it's a microsecond oscillation, 1,000 of them at the millisecond. So you have 1 millisecond to generate a state and to retrieve it and to prove that we've done something interesting. So this is a piece of engineering art that my group members have put together to make sure that this little membrane can be completely isolated from the environment and no phonons or other objects can jump inside of it and disturb the motion. Yes, I think I will have to skip this one. I think we don't have much time for that. But let me just go on. Okay, so The experimental overview, the first thing we do is we have to optically cool the system to the ground state. Those of you who are familiar with optomechanics may have read about the experiments where people cool with light mechanical systems to the ground state. So how you do it? Again, you have this oscillating device. And then what you do is the following. You can shine light, which is either red detuned from the cavity resonance, or it can be blue detuned from the cavity resonance. If it's red detuned, then the motion of this membrane will generate a sideband, which is resonant with this cavity, which has a lower frequency than the drive. So you generate light which has lower energy. Where does this energy go? This energy goes to exciting the membrane. So if you scatter a single photon into here, then you can be reasonably sure that you added a single phonon to the membrane. And now if you tune it on the other side, by the same logic, you can retrieve this single phonon into a photon which now can be detected. Okay, so step by step, as I just said, you take your membrane in 10 Kelvin cryostat, you need a very good optical axis, and then you do optomechanical sideband cooling so that you essentially are almost at the ground state, 0.2 phonons left, and now on top of those 0.2 phonons, you want to add one phonon and retrieve it and demonstrate that you have done it right. So write a single phonon excitation by low probability scattering into the Stokes sideband, condition it on a count, and read it out again and see if you have correlations between the first photon and the second photon. Yeah. This is another formidable approach. You need to detect a single photon. And the single photon comes with a price. And the price is those classical drives that you put into the system. And these classical drives contain 10 to the 8 photons. And they are tuned away from your single photon by 1 megahertz. So I invite you to design a system which can cut down the field which is away by 1 megahertz from the field of interest with the efficiency of 10 to minus 9. Well, maybe you will come up with a better system, but this is what we have done. We built 4 consecutive filter cavities with the transmission of about 30 kilohertz, and like you know, the rock solid and vertical walls in the spectral domain. Yeah, so those are the construction details, and those are the filter cavities, and those are the heroes in the lab, Ivan and Michal. Okay, so what do we observe? What do we want to observe first? We want to observe non-classical correlations between the first photon, which signifies writing a phonon, and the second photon, which reads out this phonon. So it's a G2 function, which gives you the second order correlation. And if you look at the Cauchy-Schwarz inequality, then for classical states, the 2-point second order correlation function normalized suitably should be less than 1. If the 2 states of the fields that you observe in the first step and the second step are 2 independent thermal states, it will be 1/4. If it's 1 thermal state, which you just don't resolve, it's 1/2. If it's a coherent state, then it's 1. If it's above coherent state, then it's non-classical. And the observation is 1.37 plus minus 0.3. Well, right. You can believe it, or you can not believe it. It's not 5 standard deviations, but it's better than nothing. And this is just the 2-dimensional correlation function showing that on one, you shine the first pulse and you write, and you shine the second pulse and you read, and you plot the same thing here. And those off-diagonal elements correspond to the correlations between the write and the read. And here, write and read. And they are more than, they give the Cauchy-Schwarz, which is 1.37. Yes, so those are the heroes in the lab. And it's work in progress, I would say. So I was told that the seminar is 2 hours, right? So do I have another maybe 5-7 minutes? How does it go? Well,
Sure.
the bosses say yes, so the Indians should just listen. Okay, so let me tell you a little bit of this Quantum for Life project. And one reason is kind of to flatter the Max Planck Institute, because some of our collaborators within this project involve Ignacio Sirac and his team, and we have a wonderful representative, Daniel, of this team here, who has been instrumental in putting this proposal together. So, yeah, this is just how the team is built. We have this Novo Nordisk Foundation in Denmark, and for a while they've been only funding the biomedical projects, and then somebody told them about the quantum, and they decided that they want to do some funding of the quantum science, but only if we can prove that this is relevant for biomedical applications. So we've proved it, no problem. It's a big collaboration in which our team actually are the scapegoats, because we promised to build the experiment. All others only promised to write theory papers. So let me tell you what we're talking about. So what we want to build is a system where single atomic spins are trapped inside the holes in the 2-dimensional dielectric waveguide. And the idea is that if you do it right, then if you put one spin here and another spin here, and even further away, this can, in principle, become an infinite range interaction system. So the light from one of those atoms will be guided, and in principle, guiding can be long range. And then by dialing the states of those atoms, you can tune the interactions, and in principle, you can make many of them, and they will interact, and maybe they will model some interesting system that you cannot otherwise model. So some holy grails are light harvesting, for example. Another holy grail is the magnetoreception in birds, why they can actually fly to the south or to the north, and how do they know what is where. So those are the guys, and I should especially emphasize the group leader, Jean-Baptiste Beguin, who is working on this project. So what we want is to have a collection of atoms, rather not a collection, but like, an atomic crystal, if you will, which is coupled to this 2-dimensional structure with long-range interactions, which we can dial. What is available Well, what is available, for instance, this thing is, of course, very well known and loved, and Gerhard's group has done amazing experiments in this direction. Other ways to work on atomic ensembles, Immanuel's group, of course, demonstrated fantastic achievements in generating many body state entanglement. So what we hope to do is to achieve more versatility and kind of tunable interaction between different constituents of the system by using those two-dimensional waveguides. And nobody says that it's easy, right? So all easy experiments have been already done, but this is what we want to do. And we've done, well, some other people, including Ignacio and others, have done wonderful simulations on how this can work. So depending on the spin orientation, you can have long-range interactions along different axes, and maybe you can have many of those, and they will all interact, and then you can benchmark some complicated calculations. So all that is kind of daydreaming. What we have at the moment is a system of cold atoms. So this is 4 by 4. By now we have more. They are cooled almost to the ground state of motion. At the moment, they are not trapped in the holes. So this is to address. The holes are kind of there already. We have fabricated different structures with really submicron resolution and quality. And now we have to work on loading atoms into those structures and seeing what happens. And with that, I really thank you for your attention.
Thanks for the very nice talk. I'm sure there are questions.
I was just wondering, sort of, in some of the proposals you had for gravitational wave detection, sort of, I mean, you highlighted that there's sort of a finite time during which you can do the experiment, or sort of spin incoherence. And I was wondering, how does that compare to the length of gravitational wave signals? Like, yes. So if we want to improve.
Yeah. So when I've shown the spectrum, maybe I can go back real quick. Let's do it in an intelligent way, right? So I've shown the spectrum. This is the spectrum. So, no, this is not the spectrum. But, you know, you can admire this one as well. Right. So the typical spectrum of this pulse is, for what they have observed so far, is, as I mentioned, between a few tens of hertz to a few hundreds of hertz. And so it's within this range that we care about the signal. And we need to have a coherence time of the spin, of course, which is longer than that, and we have it. And then the most difficult part for us is actually to have this spin quantum noise limited at low frequencies. This is the challenge. And we're not going to address this challenge until the LIGA people give us a lot of money and 10 more person to work on it. So the hope at the moment is to demonstrate it, just to move everything into the kilohertz range, but still demonstrate broadband reduction. Because with simple methods, for example, by injecting squeezed light into this system, you can reduce amplitude noise but of course at the expense of the phase noise. And therefore, you will be just moving this whole thing left and right. And you will not be able to reduce it over a wide band.
There's another.
I have a very general question about negative mass oscillators, in particular in the context with spin ensembles. So if I understood you correctly, you have basically an applied magnetic field, you have spins in this applied magnetic field, and you pump them basically optically to invert the spin population. So you can basically, in principle, argue that this is an effective potential, which is still quadratic because you have a restoring force which points you to your north pole.
No, where would the restoring force come from? So imagine I have all the spins here, vacuum here.
Yeah.
So that means all the spins are looking up.
Yeah.
And I have n of them. If I look in the orthogonal direction, what do I see? I see a square root of n uncertainty, right? It's like the spins are oriented this way, and I'm looking at the projection orthogonal, right? So it's a spin 1/2. It has 50.
No, basically my question is much simpler. So are you inverting the spin? So if you would stop pumping, then it kind of decays to the other direction?
Oh, of course it will. Yes, but it will take a lot of time. So, for example, I mentioned to you that this number of periods that the spin, the collective spin, will stay without any excitations if I don't shine light on it. It's 10 to the 5 periods. So it's a very, very nice oscillator. And this is achieved by placing those atoms into this spin protective coatings. But people in the meantime have done similar experiments with ultra cold atoms, achieving similar results with fewer atoms. So you just need to have good spins which live long. You need to be able to initiate them by optical pumping or other means in this direction. And you need what we call the large optical depth, which you can also refer to as cooperativity. You can have them in free space, you can put them in a cavity. But if I understand you correctly, the lifetime of the system is essentially the lifetime of the spin state.
I think my question goes a little bit in a different direction because my argument would be that you pump your system optically, and that means that the North Pole in your case is an equilibrium position or a quasi-equilibrium position.
Sure, but if I leave this thing alone in real world, in the lab, there will be collisions which will flip this thing. There will be stray RF magnetic fields, which will cause those excitations. And this is what sets, it's actually a T2 time of your ensemble, the coherence time, which happens to be, if we do it right, without disturbance and shining light, happens to be in tens or maybe even 100 milliseconds range.
So the optical pumping is turned off.
Is the optical pumping?
Yes.
Okay, then I'm fine. Yeah. I understood you that you basically.
No. I apologize. So in the simplest case scenario, the optical pumping is turned off. In more sophisticated scenario, you can keep the optical pumping on, but then your cooperativity should be large so that all your operations actually are strong. But yes, thank you.
Thank you.
Another question, yes.
Can you go back to your last slide with the array and the coupling? Or not that one?
Sorry.
That one's also nice.
But
I have not so few questions to ask.
I can give you skills. I can give you instructions. Shall we go to the talk or shall we
okay, so you have these 300 nanometer holes, and the tweezers would be focused onto these holes or to put the atoms inside?
Yes.
And there will be no diffraction effects on that?
There will. We are trying to model all that, and trying to see how you can adiabatically put those atoms there without, you have light, this light goes through those holes. As you say, it experiences diffraction. You can model those things and see what is your best case scenario. We haven't done it, Manuel, and
yeah, I just think maybe you could use some Talbot effect to use with lattices to near field diffraction to get to that periodicity that you want here. Although that 300 nanometers is not so bad for lattice structures either. So for it, how close do you want to be to have efficient coupling? I guess the coupling very sensitive.
It is exponential. It is
exactly.
So if we are, let's say, half a micron away, this is probably the limit.
And then what is the cooperativity? So how much scattering into the plane do you get?
Good question. So we found that there are actually interesting spectral resonances when you calculate the response carefully. We found that there are some amazing resonances as a function of the band gap structure and so on. We haven't seen them yet. We want to have, the 10 or something like that, greater than 5, definitely. Otherwise, you take 10 of them and things fall apart very quickly.
Yes.
So the first thing really, which I want to see happening is, let's take one atom, put it here. Let's put the tip of the, scanning atomic force microscope here and see that this atom can actually emit something that this tip can see.
But wouldn't it be even just simpler just to look at the radiation pattern of the atom? That what you could even do without a second atom. You just want to know that it just doesn't emit into 4 pi anymore, but suddenly you get this, once you approach the surface, you really get emission into the plane, and so all the emission into the...
I'm sure this will be the first run.
Would be...
You take this atom and indeed you just make a photograph of the scattering from the system. Yeah, well, one day we will knock on your door with questions.
Do you mean to do this with tightly focused tweezers to load it in?
To load, yes.
But I have a question, because the confinement along the tweezer is given by the Rayleigh range and looks like incomparable with 200 nanometers.
So the hope is that when you load them, you should do it adiabatically, right? You should have some trapping potential in play. And then, as you say, you load it adiabatically and you turn on the trapping potential. So then you can release the dipole trap and it will be only trapped by the light which propagates in the plane. It's all wishful thinking at the moment. Yes, here.
Eugene, I'm wondering, because similar things have been tried many years ago by several others. What is your magic knob that you can use to get this working?
I'm not sure to which several others you refer to. So we discussed Kimball's experiments, where it was a single, a one-dimensional alligator, and then the atoms were essentially just shot through. And well,
the idea, of course, was to trap an atom. No?
Yes, and it didn't work.
So what is your magic knob?
We work hard. We do simulations. We try to see how it works, and maybe it will work. So far, it looks like it might work. Whether it does or it doesn't, there are many things that people haven't done before.
No. This is.
I don't know. I think that we're trying to do very careful modeling, and one of the ideas is this combination of out-of-plane trapping beams, which I don't think in Kimball's group they had. They were kind of shooting those atoms through and just seeing which one of them hit the hole, essentially.
Okay. I mean, one of just a comment. One of the things that I learned, maybe over many years, 5-10 years, I don't know, is that you need a trapping potential. Yes, you have it, but you also need some cooling. No?
So you have to think about.
Yeah, definitely.
There's no cooling then.
Absolutely. Very true. Very true. No, but we'll invite you to a colloquium. We'll invite Emmanuel to a colloquium. Then we will, lock you in the room and interrogate. But sure, it's the beginning of the long road, and we'll see what happens.
Just have another question. How does the coupling strength depend on the distance now? Let's imagine you get things. Does it go like 1/² of the distance or in the plane?
You mean the distance out of plane?
No. You imagine you have, there must be some effective coupling strength.
On paper, essentially, it can go polynomially and very slowly.
Polynomially.
Yes, and very, very slowly. If we hit the exactly right wave guiding.
When you want the mode, I guess, okay, could you talk to the specific mode that has directional lobes, let's say to the one atom you want to couple to?
This is what I showed.
Right?
This is the one.
Okay,
yeah.
Okay, so these are different frequencies. You would target different modes. You would target to have
and different orientations of the spin.
On the dipoles, yes.
Yeah.
Then I can see that it will go slower than 1/².
Another question, maybe, is there one online? Okay, so I think we already had a couple of questions, and I suspect people are waiting for coffee and cake. So then if more questions come up, I think we can discuss there. So please thank you.
So there will be coffee and cake in the cafeteria. I hope it's already there. But it will come. There will be coffee and you order for 4 o'clock.